Today I will talk about local representations of metrics, and after that I will present some method of constructing metrics on smooth manifolds. Suppose that Mg is a Riemannian manifold with or without boundary. Suppose that x1, x2, xn are smooth local coordinates on the open set U of M, then it follows from our discussion about tensor fields that G can be written on U as Gij dxi tensor product dxj, where Gij with I and j varying between 1 and n, where n is the dimension of the manifold, are smooth function, and you can compute the value at P in U as follows: Gij P, this is Gp of d dx I at P, d dx j at P. From this formula you get that the matrix whose entries are these functions is symmetric because by definition G is a symmetric tensor field, and it is a smooth function of P, so it depends smoothly on P, because by definition G is a smooth tensor field. And last, from this formula where V is Vi dxi at P, V in dp m, follows that G, this matrix is non-singular. Why? Because we know that if you have 0 here, then this is possible only if V is 0. So this says that Gij is non-singular. There is an alternative notation that you can use for writing down a metric. Essentially, instead of writing G as Gij dxi tensor dxj, you can also write Gij dxi dxj. The difference between these two expressions is that in the first one you are using the tensor product, and in the second one you are using the symmetric product. Let's prove that they coincide. So Gij dxi tensor product dxj can be clearly written as 1 half Gij dxi tensor dxj plus Gji dxi tensor dxj. This follows from the fact that the matrix whose entries are the functions Jj symmetric, and this is equal also to Gij dxi some tensor dxj plus Gij dxj tensor dxi. So here I exchange the order of the indices. I can do this because remember that we are using the Einstein convention, so we are omitting a symbol of sum on two indices I and j. And this is exactly the symmetric product Dij dxi dxj. So the Euclidean metric the Euclidean metric can be written in the following way. G bar equal dxi tensor dxi, but also as a dxi dxi, that is sum on I dxi square, but also as a delta I j dxi dxj. So this is true by the Sorry, this is true because Gij is delta Ij. This is true in general. So if you have the following smooth local frame for Tm on the open set U of M, and epsilon epsilon 1, epsilon 2, epsilon n is a dual coframe that is epsilon 1 at P of EI at P of EJ at P. This is delta Ij. Then I can write G, any metric, on the open set U as Gij epsilon I epsilon j, where Gij is the smooth function such that Gij at P, this is Gp of EI at P, EJ at P. And exactly as before, you can prove immediately that the matrix whose entries are these functions is smooth, symmetric, and non-singular. It is also clear that if x, y are vector fields on M, smooth vector fields on M, then G of x, y is a smooth real value function, and in terms of any smooth local frame, locally you can write Gx y as a G I J P X I Y J. For P in the open set U you are considering. From the fact that G is an inner product, you can deduce that the length of x, that is the square root of gxx, is a smooth function on the open set where x is different from 0. Now I want to spend a few words about the notion of orthonormal frame. So suppose that E1, E2, En is a local frame for M on an open set U. Then it is a called orthonormal frame if E1 at P, E2 at P, En at P, is an orthonormal basis for TPM for each point P in U. If E1, E2, En is an orthonormal frame, this implies that EI at P EJP have an inner product which is equal to delta Ij. And this implies that the metric can be written as delta Ij epsilon I epsilon j reduces to epsilon reduces to the sum on I of epsilon I square. Frame having this property exists as shown by the following proposition that can be proved using the Gram-Schmidt algorithm. So suppose that Mg is a Riemannian manifold with or without boundary, and suppose that x1, x2, xn is a smooth local frame for Tm on the open subset U, then there exists a smooth orthonormal frame E1, E2, En on U, having this property. The space spanned by the vectors E1, E2, En at P coincide with space spanned by x1 at P, xk at P, for any k varying in the set to 1, 2, 3, n. And of course, for each P in U. So this says that for every P in M, there exists a smooth orthonormal frame to find, okay, let's write E1, E2, En to find on some neighborhood of P. Here, smooth means that the local frame E1 at P, E2 at P, En at P depends smoothly on P. Now, before presenting the first method for constructing metrics, I want to talk about a special kind of maps known as isometries. So suppose that M and G, M tilde, G tilde are Riemannian manifolds. With or without boundary. An isometry from Mg to M tilde G tilde is defined to be a diffeomorphism phi between M and M tilde such that phi star G tilde coincide with G. What you have on the left side is the pullback of G by, of G tilde by phi. This is a metric on M, and we are saying that we want this metric to coincide with G. Let's maybe see how it is defined, this pullback. If VW are in TPM, then phi star G at P of VW tilde, this is just G tilde at phi P of d phi at P of V d phi at P of W. In this case, I mean, if this map exists, we say that G and M tilde D tilde are isometric and I want to give the local version of this definition. So we have that a map phi from M to M tilde is a local isometry if each point P in M has a neighborhood U such that phi restricted to U This is an isometry. Okay, the first method for constructing Riemannian matrix is the one consisting in looking at matrix which are inherited by some manifolds of a Riemannian manifold. So let's start presenting a lemma whose proof is easy and which says the following. So suppose that this is a Riemannian manifold with or without boundary. Suppose that F is a smooth map where M is a smooth manifold. Then we have that the smooth tensor field G equal F star G tilde, that is the pullback of G tilde by F, is a Riemannian metric if and only if F is an immersion. The proof, I think, it's clear, because if F is an immersion, then its differential is an injective map, and when you compute this pullback, you will get that the tensor G is this way an inner product on the tangent space TPM of M. Now, suppose that We have such a map. The metric G equal F star G tilde is the metric induced by F and if on the other end the manifold M is equipped with a given metric, an immersion or better an embedding which satisfies G equal F star G tilde is called isometric immersion or isometric embedding. The reason why this adjective appears is clear and it follows from the definition of isometry. Now, what are the most important examples of induced matrix? That is a matrix of this form here. Suppose that M is not just a smooth manifold, but M is an immersed or embedded submanifold of M tilde then this means that you can consider the special case where F is I the inclusion map, and in this case you can have you have the metric G equal I star G tilde. M equipped with the I star G tilde is what we call Riemannian submanifold, and this is true not only in the case where M has no boundary, but also in the case where M has a boundary. From the definition of I star G tilde, you get that for each P in M, for each VW in TPM, GPVW equal I star G tilde PVW. This is nothing but then G tilde P di at P of V di P of W. Now if you make the following observation, DIP sends this space into this other space, and we usually identify DIP TPM with TPM, and we think of the IP as an inclusion again. Then this says that GPVW is nothing but then G tilde PVW with VW in TPM. In other terms, this says that this metric is a restriction of this metric here to TPM. A priori, this is defined on pairs of vectors of TPM tilde, but here we are saying that we look at the action of GP tilde only on pairs of vectors of TPM. So in this case, the case of Riemannian submanifolds, the induced metric is the restriction of the metric of the ambient manifold to vectors which are tangent to the submanifold. Examples. The basic examples is given by the unit sphere Sn of Rn plus 1. The Riemannian metric induced on Sn by the Euclidean metric this is denoted by G circle. This is known as a round metric or standard metric on Sn. In the other example I will present, I will use what we call smooth local parametrization. So let's say some words about it. Suppose that as before, M is a submanifold of M tilde, then a smooth local parameterization of M is a smooth map X from U to M tilde, where U is open subset of Rn or Rn plus. We are in this case, if the manifold M has no boundary, we are in this case if the manifold has boundary. Such that X of U is open in is an open subset of M. Now, if we set V equal X of U, phi X inverse from V to U, then V phi, this is a smooth coordinate chart for M. And what can you do with this map? Suppose that there is a metric on M, precisely the induced metric, then you can get the coordinate representation of G in the coordinates let's say induced by the local by the smooth, let's write properly, local parametrization. X. So precisely you can write phi inverse star of G. This is essentially the X. I define phi as X inverse. So this is X star G. But by hypothesis, this is a Riemannian submanifold. So G is given by X star I star J tilde. And this is just I composed with X star V tilde. And since this map coincides with X, this is just X star G tilde. Let's see some example. The first one is the one where M tilde is Rm, and the M is an immersed n-dimensional Riemannian submanifold of Rm and x from U into Rm is the smooth local parametrization of M. So what I want to do is to see what is this metric here. The symbol that we use for the metric is this, because we are using the Euclidean metric. So what I have to compute is x star g bar. You remember the formula for the pullback, and you know that G bar is sum on I dxi square. We assume that x has the following component: x1, x2, xn. This is true because X is a map in Rm. As a consequence, what happens when you compose G bar with the differential of this map? You get sum on I of dxi square, and what is this? I need more space, so I will continue here. So we have to compute this. If U1, U2, N are coordinates on U, you have N coordinates because this is smooth local representation of M, which has dimension N. So this is sum on I of sum on J from 1 to N of dxi duj squared, and this can be written as sum on I of sum on j and k from 1 to n of all possible products. So I have dxi duj dxi duk duj duk. So this is a formula for the metric on the submanifold M written in terms of the coordinates on U. Example number 2. Matrix in graph coordinates. So suppose that you have an open set, a smooth function f, then you know very well that the graph of f is the set of points of the form x f of x, where x is a point in U. You can prove that gamma f is a submanifold, is an immersed submanifold of dimension n, and it has a global parameterization x which is known as a graph parameterization given by this formula, and where, so let's write here graph parameterization and U1, U2, UN are the graph coordinates So what is the metric induced on gamma f by the Euclidean metric of r n plus 1 in terms of these coordinates? Also in this case we have to compute x star of g bar, where g bar is the Euclidean metric. The difference with the The previous case is that you have m equal n plus 1 and x of u1, u2, un plus 1. This is equal to u, sorry, it's right, I, for I equal 1 to n, and x n plus 1 of u1, u2, un plus 1 is f of u. So if you apply the formula I raised, you will get just du1 square plus du2 square plus dun square plus df square. Let's check the time. Okay. The next example is the surfaces of revolution. Suppose that you have the half plane H. H is defined by this. So this is a half plane. Half plane. And this line here corresponds to r equals 0. Suppose that C contained in H is an embedded one-dimensional manifold. Then the surface of revolution determined by C is SC the set of points of coordinates x, y, z such that square root of x squared plus y squared z belongs to C. Essentially, if this is a C, SC is the object, actually a surface, that you get rotating around the line r equals 0, this half plane. Suppose that C, which is called the generating curve, as the following smooth local parameterization gamma t equal A of t B of t, then you get a smooth local parameterization for SC x t theta equal A of t cosinus of theta A of t sinus of theta B of t. Of course, there are some restrictions on the range of t and theta, but it's not important for us, because what we want to do is to compute the induced metric on SC. Once again, we have to use the same formula, x star g bar, where g bar is the Euclidean metric of R3. If you apply the formula I presented before, you will get d of a t cosinus theta square plus let's write this way, plus differential of a t sinus of theta square plus d of b of t square. And the final formula is a prime t square plus b prime t square dt square plus a t square d theta square. It's clear from this formula that if C is parameterized by arc length, or in other terms, the speed of gamma is equal to 1. Like this, then you get that x star g bar is just dt square plus at square d theta square. This formula allows us to get immediately the metric of the unit to sphere of a torus of revolution and of the unit cylinder, for example. So let's see some detail. If you take C equal to R Z such that R square plus Z square equal 1, actually I should be more precise than that, because I cannot take all the circle. If this is H, what I'm doing is, what I have to do is to take an alpha circle of radius 1. This can be parameterized by gamma phi equal sinus of phi cosinus of phi, with phi varying in the range 0 pi. It is clear that gamma prime has a length equal to 1. So we are in this case and this formula implies that the x star g is given by d phi square plus sinus square phi d theta square, and the reason why this is true is that t now has been replaced by phi, and x of phi theta is sinus of phi cosinus of theta sinus of phi sinus of theta cosinus of phi. This is a very well-known formula, but I prefer to write it for the sake of completeness. This is what we call spherical coordinate parameterization. So this is the metric of the two spheres written in in terms of the local coordinates phi and theta. Let's talk about the torus of revolution. For the torus of revolution, we can take C to be the circle of equation r minus 2 square plus z square equal 1. This can be parameterized by gamma t equal 2 plus cosinus of t sinus of t. What we are doing in this case is that we are taking a circle of radius 1 centered at the point of coordinate 2, 0. So this circle does not intersect the line r equals 0. Also in this case we have a map which is parameterized by arc length, and the formula I raised, that is dt square plus a t square d theta square, reduces to dt square plus 2 plus cosinus t square plus d theta square. Last example, number 3, is the unit cylinder. In this case we take C to be the curve gamma t equal 1t. This is a vertical line and clearly this is parameterized by Ackland, so we get that SC is the unit cylinder, and the induced metric is dt square plus d theta square. Let's stop here. Thank you for your attention.